welcome to my channel, Web3 Mind, and today's topic will be transparent upgradable proxies. So right here we have the proxy pattern, and for this pattern, or for the standard, we have the proxy, the user, the proxy admin, and the implementation. So from a user perspective, the user will call the proxy, and inside the proxy there will be an owner address that is stored as a constant. And so every single time someone calls a contract, it will reach the fallback because there is only one external function inside this proxy contract, which is the fallback. So it will always reach the fallback, and then inside the fallback, they will compare the caller's address with the owner of the proxy. And if it's not the owner, then it will go ahead and delegate call to the implementation. On the other hand, if it is the owner, so in this case, the proxy admin is the owner, it will reach the fallback, and then it will check that it is the owner of the address. So the proxy admin will equal the owner of the proxy contract, and then it will go ahead and run the upgrade logic. And the reason you want the owner to be the proxy admin is because it's stored as a constant variable. So instead of having the owner stuck like to one address, you have it behind a proxy admin, and then the proxy admin will handle transferring ownership to another address or to a multisig, etc. And also the reason you want to store it as a constant is because reading from the bytecode of the contract, so a constant variable, is cheaper than reading from storage. But if you are familiar with proxy patterns, you know that according to the standard, they store the address of the owner, so the address of the proxy owner, in storage as well. So in the transparent upgradable pattern, you'll actually store the address of the owner in two locations, in bytecode and also in storage. In storage, it's actually just there to follow the standard, so that whenever a scanner like Etherscan, or to easily access from the outside, so like you want to find out who's the owner of this contract, you can easily read from storage. But the actual address that is used to compare to is stored as a constant variable. So there is a small, you can almost 100% trust that the address in storage and the address in stored as a constant will be the same, but there is the possibility that the owner could change the address. So that is one thing to note, but that should not happen unless the developers are malicious or just make a very, very bad mistake. Okay, so hopefully that makes sense, and if it doesn't, then hopefully looking at the code will clear things up. Okay, so right here I have a blank project, and we are going to use Forge for this, or Foundry for this example. So let me go ahead and put it into presentation mode and make everything a little bigger for everyone. So let's run Forge init -- force, and this will just initialize a Foundry project, and then let's install Openzeppelin contracts. Install Openzeppelin /Openzeppelin dash contracts dash upgradable. So this will install Openzeppelin's upgradable contracts. Okay, very, very nice. And then do Forge install Openzeppelin /Openzeppelin dash contracts, and this will install Openzeppelin's normal contracts as well. Okay, very nice. We have them both installed, and then we can go ahead and go in here, and you can see that we have just the basic template for a Foundry project. So for this example, we're going to have different versions of the counter. So we're going to run through the upgrade process of like starting with version 1 and then go to version 2, etc., etc. And for this, we do not need the script file, so let's go ahead and delete that. So just go ahead and delete that whole folder. And then also inside the foundry.toml, we are going to have some remappings to make our lives easier. So remapping equals inside brackets, and then I'm going to copy this from the Openzeppelin website This will be, the link to this will be in the description, and also I'll probably just put the actual copy and paste stuff in the description so that you can easily follow along as well. Okay, so that's the first part, and then one more thing I need to add into the remappings. Okay. Very nice. Okay, that is done. Let's go ahead and save that and run forge build to make sure everything is okay. Forge build, and as expected, everything is okay. And so, for the first version of our counter, we can go ahead and rename this to version 1 so that we can easily differentiate between the versions that we will be using. So let's go ahead and rename this counter v1, and then actually we'll have to change the import here as well. Counter v1, and then also v1 here as well. 1, and then v1 as here. And then counter, let's go ahead and change this as well to counter v1. And then this one, let's do counter, whoopsies, counter v1 equals new counter v1. And we can delete this next line, and then actually let's go ahead and delete all these functions, all these tests right here. Okay, now we're ready to start. So for this version of the counter, whoops, I forgot to rename this, so let's rename this file actually counter v1. Very nice, and it should fix that error right there, that warning. Let's run forge build to make sure that our imports are working correctly, and they are. Okay, even though it's red underlined, it should be importing correctly. Sometimes it does that. Okay, so for this version of counter, so the v1 version, it is a very, very simple contract, as you can see, very, very short. There's not too much to change here to make this contract upgradable. There would be some things when you need to change if there was a constructor, but as you can see, there's no constructor, so let's just go ahead and deploy this. So first things first, we need to import Transparent Upgradeable Proxy, and this will be from the Openzeppelin library. /transparent, and then /transparent upgradeable proxy. It's very important to spell everything correctly. .sol. Perfect. Okay. Hopefully that is all correct. And then, now that we have deployed or imported this, let's go ahead and create a variable for it. So let's do transparent. Let's actually just copy this instead of typing it over. Transparent upgradable proxy, and let's just call this let's just call it contract proxy to keep it simple. Okay, contract proxy, and then this will be our B1, and then this will be our contract proxy. So whenever you're deploying a transparent upgradable process, it will go like this. First, you need to, number 1, deploy the implementation contract, and then 2, deploy the proxy. And actually, that's all there is to it. That's very, very simple. So as if you remember from the diagram, there's actually the proxy and also the proxy admin. So we took care of the implementation and the proxy. So this is, the implementation would be considered counter v1, and then the proxy would be considered this transparent upgradable proxy right here. But if you remember, there's also the proxy admin, and that is actually handled by the transparent upgradable proxy contract. So if you look at the code inside go to the lib, go to Openzeppelin contracts, go to proxy, and so Openzeppelin contracts, and then inside of contracts, go to proxy, and then go to transparent, and then right here, let's click on that transparent upgradable proxy. If you go here and you go to the constructor, whenever this is deployed, you pass the address of the implementation contract, or here it's called the logic, so the address of the logic, and then you pass the address of the initial owner, And then you also pass some data, which we haven't talked about yet, but this would be used to like initialize functions whenever you're first deploying. But for the first version, we won't touch this, but the second version, we will have to worry about this. Okay, but so the initial owner, and what I was pointing at is that they actually deploy the proxy admin right here in this first step. So the initial owner will be the owner of the proxy admin, and it will deploy its own proxy admin, and then it will actually put that address into storage and also write in an immutable variable right here. So the admin right here, the address private immutable. And if you're familiar, immutable and constant are both inside the bytecode of the contract. And yeah, so that's where that is taken care of. Let's go back to our test now that that's clear. Okay, so first things first, we deploy the implementation contract right here, and then let's deploy the transparent upgradable proxy. So let's copy this and let's do this, and then set it equals new transparent upgradable proxy. And then the first parameter will be the address of the implementation, so the address of counter v1, and then the address of the owner. Okay, and let's go ahead and create an owner right here. So address owner equals make addr, and let's just make an owner. If you're not familiar with Foundry, this is just cheat code within Foundry, and we're making an address that we can later use owner, and then we'll pass this right here. And then the third parameter, if you remember, was the init data, which we will just leave blank for now because there is no there's no initialization involved in this counter. Okay, so that's actually all there is to it. So that's about as simple as you can make it. I mean, if you start adding things and you start upgrading to V1 to V2, it gets more and more complicated, but that is probably as simple as it gets right there. And so let's just run forge test, and I'll run the setup function. Actually, there's no tests to run, so let's just write a dummy test, and let's just call it run setup. Okay, and then just do public, and then let's just do run the setup. So we'll just run this test, which will run the setup. Forge test dash empty for match test, and then paste the test name dash bbb to print out anything if we get any errors, to print out some messages. Okay, and yeah, perfect. So it was successfully deployed. And we have the contract proxy. And then you might be wondering, so this is the transparent proxy type, so how do we call the functions on this? Because it's supposed to represent this function, or this contract right here. So to do that, it's actually very simple. Since we have the contract, we can actually just typecast the contract proxy to the counter v1 contract. So let's just rename this test to test. Let's increment. Okay, let's run test increment, and let's get this contract proxy. So I get this proxy, and then we will typecast it to counter v1 dot increment. Perfect. Okay, counter v1, we call the increment function, which will add 1 to the number. Perfect. So counter v1, and then before you pass it, you have to convert this to an address. So we convert the contract proxy to an address, and then convert the address to a contract type of counter v1, and then we call the increment function. So after the increment function is called, let's go ahead and assert that it actually was incremented. So do that, and then we can do this. Might be beneficial to save in a variable, but for now we'll just do this. And then we'll read the number. Since it's a public variable, we can just call it like this, read it, And then let's just check to see if it was equal to 1. And let's run this test. Okay, let's run this test. Forge test dash empty. And perfect. So the test passed. So the counter was incremented and the number was equal to 1. And actually I will run that test again with 4 V's to give lots of information. So you can see right here that the assertion was 1 is equal to 1, which is true, and the test passed. Perfect. Okay, so that's very, very simple. So let's go to make it a little more complicated and create a version 2. So actually let's create a new file. Let's call this counter v2.sol. Nice. And in counter v2, let's copy all counter 1. Let's paste in v2. Perfect. Okay. And inside here, let's add the functionality as if the contract had a constructor. So when you're normally deploying a contract, you might want to have initial variables like, say, uint 256 initial number, something like this. So you have the initial number, and then you want to set the number to the initial number. So initial number, perfect. So you want to do this, but this will not work. All the storage is held in the proxy contract, and whenever you're deploying the implementation logic, the constructor will modify the storage of itself. So that's going to do us no good. It's actually not going to modify the storage of the proxy contract, which is what we want. So this will pretty much do nothing. I mean, do nothing, and then worst thing, you think you actually did something and you expect it to happen, and it's not really there, and then you just create a bunch of problems for yourself. So the way to get around this with proxies is you actually use something called initialization function. So you're actually going to import an abstract contract from Openzeppelin to help us do this. So it's initial, and the contract name is initializable. Initializable. Make sure you spell that right. And then that will be from at Openzeppelin /contract /proxy, I believe, /utils /initializable.sol. Okay, hopefully that is correct, and if not, it'll give us some warnings, but it looks okay. And then we want to do counter v1 is initializable. Okay, counter is initializable right here. So now we have access to the functions from that contract. Let's run forge build just to make sure everything works. Forge build, perfect. Everything's working. Initializable. First things first, you want to add a function called initialize. Initialize, and I'll tell you uint 56 initial number, and this will be public, of course, there. And actually we'll add a modifier initializing, I believe it's initializing or initializer. Initializer. Okay, yes. So the modifier name is called initializer. And then inside the initializer, you'll do almost exactly what we would have done if we were doing in a constructor. So we set the number equal to the new number, or the initial number, actually. And let's put a semicolon there. Perfect. Okay. And also, this is a good practice to disable initializers in the implementation contract. Usually it's not a problem, but there was a bug in the past with, I think, one of Openzeppelin's contract libraries. I think it was version before version 4, somewhere around that. Anyways, you want to disable initializers. Disable initializers, and yeah, we're not gonna use this, so we can comment out there so you can remember what it's supposed to look like. Okay, so this should be good. So this will handle the constructor. So this will be like a constructor for a proxy contract. So how do we do this? How do we call this, and how do we upgrade to version 2? Well, I will show you. So function, let's create a function that will upgrade to version 2. So let's just call this upgrade to v2. And let's do this as an internal function. Okay, internal function. And first things first, we actually need to import the new contract that we just made. So import counter v2 from /src /counter v2.sol. Perfect. So now we have counter v2.sol, and it's giving me an error because I probably forgot to rename it. So okay, yes, this needs to be counter v2. Counter v2. Perfect. Okay, let's see if that error's gone. Yes, eventually it'll disappear. Okay, yeah, it'll probably disappear eventually. Well, let's run for build. Oh, perfect. So yeah, built, but still get that error. Anyways, just ignore it. Get this counter v2, and we need to deploy upgrading steps. 1, deploy the new implementation. So 1, deploy the new implementation. 2, you need to call the proxy. It's called proxy admin contract. Call the proxy admin upgrade function. And then 3, proxy admin, or you could call this like 2a proxy admin will forward the call to the proxy and upgrade. Perfect. So we call the proxy admin. So only things we really need to do is deploy the new implementation logic, call the proxy admin upgrade function, the necessary data, and then from there the proxy admin will call the proxy contract and upgrade it. So let's actually look at the actual proxy admin contract so we can know what to call. So if we go back to where we just were, so lib Openzeppelin contracts, transparent proxy admin, click on this, and let's just put this over here for reference. Let's see how, okay, so this is the function we need to call right here. So it's a public payable virtual owner, only owner, which means that we can only call it with the owner that we initially set, which is right here. So we need to call this upgrade and call, and then as parameters we need to pass a address of type Transparent Upgradeable Proxy, and address to the implementation, so the new logic, and then also the bytes memory data, which will be the initialization data. And for our upgrade, the initialization data will include, if you look right here in our initialize function, it will include the initial number, and I will show you how that all works. So let's go ahead and get this out of the way. So first things first, deploy the new implementation logic, counter v2 equals new counter v2, and there's nothing we need to pass. Perfect. And actually, there we go. Okay, counter v2, and then we need to call the proxy admin. And I don't know if you're wondering, there's one thing we're missing, is where is the proxy admin's address? Like, remember, we deployed it in the setup function. So we deployed the conjug proxy, and we have the proxy, but we do not have the proxy admin. So we're missing the address. And according to the standard, the EIP 1967 standard, the proxy address is actually stored in a very, very specific location in storage. So I will show you that. If you go to the Openzeppelin contracts and then you go down to contracts, then the proxy, and then into ERC 1967, and let's go to ERC 1967 utils, and you'll see right here actually is the implementation slot. So this is where the address of the implementation is stored, which is something else. We're not right now, we're looking for the admin. So let's keep looking for the admin. Implementation. Ah, here it is. So there is the storage slot for the admin. And if you are familiar with storage, usually the compiler will decide your storage automatically based on the order that you declare variables, but we don't want this in just any location. We want to always know where it is, and so instead of just putting it in slot 0, etc., or slot 2, whatever, they actually put the admin's address in a certain location, which is the kecak 256 hash of the string EIP 1967.proxy.admin subtracted by 1. And you may ask why it's subtracted by 1. It's just so that it creates a more random location. So it's very, very unlikely to hash with any other storage variables. So we can actually just copy this. So let's copy this for our own convenience and take it, copy it over, and we'll go ahead and paste it into this function for reference. Okay, and these comments are probably going to throw some errors, so let's go ahead and delete these. And let's delete this, and delete this. And let's leave this here for reference. Okay, very nice. Very nice. And let's save this, and internal constant, we need to change this to just bytes 32, admin slot. And we can just call this admin slot, so it won't throw us any errors. Okay. Now that we know where to find the address of the admin, we have to read it as well, and we can do that by doing vm.load. And actually we need load takes two variables, the address or the contract that you want to read from, and also the slot. So address, this one, contract proxy, address contract proxy, and then the storage location, which is what we just copied right here. So admin slot, and there we go. But VM load will actually read 32 bytes from storage, so we will save that here, bytes 32 data. Let's just call that data. So we're reading the address from storage, but 3 S's. Okay, we're reading the address from storage, but it will not actually return the address. It will actually return 32 bytes. But to get the address from those 32 bytes, we can take the data, and then we can just cast it into an address. So let's do that by like this, address proxy admin equals uint256. First, we have to cast the bytes 32 into uint256. Then from uint256, we can cast it to uint160. And then from there, we can cast it into an address. So, the reason you have to do this, if you remember, if you know bytes 32, you have to first cast it to a uint56 because uint56 is 32 bytes, and then from there you have to cast it into uint160, which is 20 bytes, and then from there you can cast it into an address, which is also 20 bytes. So that's the reason you have to do that. Okay, so now we have the proxy admin, we can call the upgrade logic on the proxy admin contract. And to make our lives easier, we will go ahead and import the proxy admin from the transparent upgradable proxy. And hopefully that works. Yes, that's perfect. So we import it from the same location, transparent upgradable proxy. So we have the proxy admin here. And we go ahead and typecast this address to type proxy admin so that we can easily call the functions on it. Okay, so proxy admin dot supposed to be capital P, proxy admin dot upgrade and call, I believe. Upgrade and call. And let's double check to make sure that is correct. So let's go back to the proxy admin, and you have it upgrade and call, and yes, that is correct. So let's go back to the test, upgrade and call, proxy admin. Why is it giving an error? Okay, because we passed no arguments. Let's get to that. But first, here, let's go ahead and import transparent upgradable proxy from there, because we need, if you remember, we need to pass address of type transparent upgradable proxy. So to do that, we will import this and then typecast the address to that. Okay, so first parameter will be transparent upgradable proxy of the counter contract proxy. So let's type address contract proxy, and that will be the first parameter. And for the second, it'll be the address of the new implementation. Address counter v2, and then the last is actually the initialization data, which we still need to create. So I'll just put a placeholder, but this actually needs to be declared before it because we will need it to exist. Okay, so move that up there, the counter v2 up there. And let's create the initialization data. So this will be bytes memory init data equals abi.encode with selector, abi.encode with selector, and then we'll do counter v2 dot initialize. And no, we don't want that. That's just not right. Initialize dot selector, and the args will be our initial number. So uint 256 initial number equals, let's do this. It's version 2. Let's just do 222. Nice, and let's correctly spell this initial number and put 256. Nice, initial number 256. Uint 256 222, and paste this right here. And now we will have the initialization data. So we take this initialization data and put it right here, and we should have successfully upgraded the contract to version 2 when we call this function. Okay, let's actually go back to counter v2 and let's add one more function. So let's call this function, and let's create a decrement function. Increment and public, and then we will just have it decrement the number by 1. Okay, let's go back to the counter t.sol in the test folder, and let's run forge build to make sure everything compiles correctly. Perfect. And then let's add another function called function test. So this will actually be a real test. And upgrade to v2. Okay. Now let's make it public. And inside this function, let's call this internal function. Okay, this should upgrade the function, this should upgrade the proxy to version 2. And after the upgrade, the proxy should actually have the decrement function available, and also the initial state, or actually the initial number, should be set to 222. So let's make sure that is all good. So let's do assert.equals, and let's get the proxy contract. So contract proxy. That's it, correct? Yes, contract proxy. Contract proxy. And we actually, let's typecast this to, because now it should be at least counter v2. So let's cast this to counter v2 contract type, and let's read the number. So this number should be the same as our initial number we set right here. So let's just copy this 222, put this here, and this should be correct. And of course we have to first cast this to an address before we cast it to another address or another contract type. Okay, now let's run forge test -- empty for match test, and then the test name. Test name, paste, and let's put VVV to print out any errors. Oh, yep. And so we got an error because we are just calling this contract as a random user. And if we're calling as a random user, we're not going to be able to upgrade it. It's going to unauthorized account, of course. So you're not authorized to upgrade this. So we need to prank call the contract as the owners. Actually, let's put this vm.startPrank inside the upgrade v2 function. So let's put this here. And let's just put it at the very beginning, vm.startPrank owner, and at the very end, let's do vm.stopPrank. Perfect. Okay, now let's see if that worked. Let's run the same test. And perfect, the test passed. And let's run the test again and add a fourth v so that we can see the output. And then you can see right here that 222, so it read the contract number is equal to 222. Perfect. So that we know that whenever we sent this initialization data, that it was successfully ran the initialize function, and the number was set to an initial number right here in the initialize function. Perfect. And then let's actually test one more thing. Let's make sure that we have the new functionality added to our contract. So actually, let's do first decrement. Okay, and assert that the current number is equal to 221. Okay, let's run the test again. And perfect. So 221, 221. So we successfully upgraded the contract to version 2, and we successfully set an initial value for the number in the initialization function, or the initialize function. Now let's upgrade to version 3. So let's create another file, counter v3.sol, and let's copy everything from version 1 and let's put in version 3. Okay, so we have an initialization function, and for this time we actually need to change the modifier. Since the contract has already been initialized, we need to change this to read initialize, and and then this actually takes a parameter which you can think of as the version number. So since we didn't use it here, it kind of skipped this version. So you could say counter v1, it skipped the version, but then counter v2, we initialized it. It set the contract version to version 1. It actually is version 2. And then here we actually need to run the reinitialize. We need to use the reinitialize modifier and pass a version number. And to make it more consistent, I'll just go ahead and skip a version and then just put 3. And why are we getting that error? Let's check. Let's see. Initializer, that's the one we used earlier. And then reinitializer. Okay, not reinitialize, but reinitializer. So with the R at the end. Perfect. And let's add another number. uint256 public. Let's just call this our second number. And let's copy this, and then let's actually initialize our second number address. Second number. Okay, second number, and then let's set our second number equal to the second number that we are going to initially set it as. So just do something very, very simple. Okay, second number. Why did I type address? uint56. Perfect. So we added a new variable. We added another number inside the initialize function, and that's it. So let's just do that for version 3. And then let's write another function at the very bottom. Let's just write one similar to upgrade to v2. So let's just copy all this, paste it. Actually, first let's finish the naming. Upgrade to v3 internal. Okay, nice. So we copied that, and let's go ahead and import the counter v3 from /src/counter v3 dot sol. And I think I probably forgot to update the naming again. So let's check it. Counter v3, and yes, I did. Let's rename this to counter v3. Nice. Okay. Counter v3, and it should all be good. And let's go down to this one, and let's update it accordingly. The owner was the same owner. We can leave that. The admin slot is the same slot, but let's rename this to counter v3. Let's do this counter v3, and then counter v3. Okay, and the initial number would be this, and then we need to add another uint256 initial. Let's just do second number equals, let's just call it 333 init byte data, initial selector, and I'm going to change this to 3 initialize selector, and we actually need to pass another one right here. Pass the initial second number here. Perfect. And then the proxy admin will be the same. This will be the same. And the proxy admin upgrade and call transparent upgradeable proxy address. So this is all the same. And then, but we need to change this to counter v3, and the new init data also the same. Leave that there. And we can create another test to test that the upgrade is successful. So function, copy this, function test, and just do v3 public. Okay, and let's run this function, upgrade to v3. Perfect. Okay, and let's just do forge test dash match test upgrade to v3, upgrade to V's to print out any errors that we get. Oh, perfect. So we upgraded to V3, just like that. And now we're in V3 already. And this one was actually, no, we didn't really change anything except for adding a variable into the initialization function. So, and also, yes, we changed the reinitializer. We started using the reinitializer. So, only for the first time that you use the initializable contract, you use the initializer, and then any subsequent versions you use the reinitializer and set the version number here. And if you want to prevent it from ever being initialized again, you can actually set this to 2 to the power of 64, I believe, minus 1, and that will put it at the max version allowed and will no longer be able to initialize. Let's actually double check that. So let's double check what I just said. Reinitializer, and yes, 2 to the power of 64 minus 1 will prevent any future reinitializations. Nice. Okay, so that is pretty much the basics of the transparent upgradable proxy, but I wanted to point out some caveats, and this is not just specific to transparent upgradable proxies, but just proxies as a whole. Let's declare a uint256 array of size 10 right here, uint256 size 10, and let's just call this my numbers array, and we won't declare anything inside this, so it should be like an array of size 10 0 0 0 0 0. And if you're dealing with proxies, you definitely do not want to do this. This is bad. This is bad. Okay, so version 1, version 2 is okay, we did everything correctly, but version 3 we did something very bad. We added a variable before our original variables. Whenever dealing with proxies, you always want to add variables at the end. You can't, if you add a variable at the beginning, then you will have storage collisions. I mean, it will be a given pretty much. If you start putting variables before each other in versions or subsequent versions, then you will have storage collision, and this storage will collide. And if you want to see what I mean, I will show you. Okay, I made a mistake in this step. Let's actually, so if we do this, we're actually directly upgrading to version 3, which is not a big deal, but to be more consistent and to show how you upgrade from version 1 to 2 to 3 and not just 1 to 3 and 1 to 2, we need to actually upgrade to version 2 before we upgrade to version 3. So let's actually upgrade to V2 and then to V3. And let's run that test again. Test -empty and 3 V's to print out any errors that we get. And perfect. So yeah, there's no problem there. But it would, yeah, there's no problem there. So, but I wanted to make it more clear that we're starting at version 1, which is set up in the setup function. And then from 1, we're going to 2 and 3. Perfect. So the only thing we changed here is we added an array of size 10, a constant size 10 of uint256. And this should be 0. This is bad. This is bad. This is a new variable. Is a new variable and should initially be 0. But will it really be? Okay, this is a new variable and it should initially be 0, but will it really be? Here in the initialize function, we're setting the initial number to the ones we pass in the call data, but we are not setting this to anything, so this should be 0. We just added this in version 3, but will it really be? So let's find out. So we will upgrade to version 3. So upgrade to version 3, and then let's try to read the array. To make this public, it should be, by default, it should be public, but let's explicitly declare it as public, and let's go in here, and let's get the contract proxy, contract proxy, and let's typecast this to counter v3, and of course we need to first cast it to an address dot my numbers array, and I believe you can just pass this in. So let's get the my numbers array at location 0, and let's just console.log this. So let's do console.log this value. One console.log this value. Let's do this. Oops. And that's forge test dash match test name dash 1 2 3 v's to print out the console.log. Okay, perfect. And so you can see that at location 0 we have 222. So the first value in this uint56 array that we just added in version 3 is 222. And why is that? It is because, if you remember, initially we set the number in version 2. So in version 2, we set the initial number to 222. And that set the number right here to 222. And this number is in storage slot 0. Storage slot 0. And if you go to version 2, the first number in this array, it will be storage slot 0, sorry. This will be in storage slot 0, the first number of this array. So the first number in this array will actually be the old value of this number. So we just had our storage collide. Okay, and actually there's one last thing I wanted to point out before I ended this video, and that is when you are inheriting other contracts. So as you saw, we are actually inheriting the initializable contract here, but they actually handle their storage in a very unique way. So if you see here, they're a reinitializer and they are getting their storage variable, or their storage location, sorry, from get initializable storage. So we can follow that to here and get the initializable storage slot. So they're getting that, which is, where is that? Let's search it, and it is here. So they are doing a process what's called namespace storage. So they are storing the initializable data inside, well, at this storage location. kecactive56 ABI encode uint56 kecactive56 Openzeppelin dot storage initializable -1, and that's how they determine this, and then just go ahead and place that constant here. So they are storing it in very specific locations, but when you're a developer, you usually don't do that. I mean, you can, it's probably best practice too, but it's also very complicated, and you also have you need to have functions to get the storage, and so this will return the storage pointer, and then you can, from the storage pointer, you can access the different variables that are in that storage slot. So the way, usually for simplicity, developers will actually leave a storage gap. So let me show you how that works. So let's make a new contract, and let's call this let's just call this counter parent.sol, and this is just a very simple contract. Let's just copy this, doesn't really matter what it is exactly, and let's just rename this to counter parent, and parent stuff, parent number, let's rename this parent number counter parent. Let's do this and do counter parent number dot increment, and set parent number. Let's rename these functions because we're going to import them, so we don't want to have function clashes with the same name. So let's just say our parent number, increment parent. Okay, so we just changed this function just a little bit, and the main purpose is just to show you how to handle inheriting other contracts. So let's go to counter v1 and let's import counter parent from dot counter parent dot sol. Perfect. So counter parent, and then let's inherit it by is counter v1 is counter parent. Okay. So let's say in version 1 you did not have this. So this did not exist. This did not exist, and then you added a parent contract like this is parent. Then all your storage variables are going to be moved down. So 0. So storage starts at 0. So this will be storage slot 0, and then this will be 1, etc., etc. And so whenever you're declaring or in a parent contract, and then say you upgrade this, you upgrade the parent to a new version, and then you add another variable like Unit56 public new another number, just another number. Okay, another number. So let's say you add another number, and then you are shifting the storage slots down again. So this is now 0, 1, and then in the counter v1 contract, this will actually now be slot was it 0, 1, 2. So this will be slot 0, and so on. So if you add another one here, then it will move this down to 3, and then you add another one, another one here, and so you go 0, 1, 2, 3, and then after that, this one will be the next slot. So to get by this, usually what developers do is they declare Unit56 an array of Unit56, because Unit56 is 32 bytes, and every storage slot is 32 bytes. So every number in this array, or the size of this array, will be equal to the amount of slots that it will take up. So let's say usually they do about 50. So Unit56, and that will leave a storage gap. So this is just a blank array, like you can usually call it storage gap. And so whenever you add a variable here, so let's say this is version 1, so you have it, and then you have a storage gap here, and then counter v1, you're inheriting the counter parent, and this will no longer be true, so we can get rid of this. So you inherit the counter parent, but then you want to add, you make an upgrade, and you want to add a variable to the counter parent. Then you go ahead and add another variable. So Unit56, let's say public another my third number, let's call it my third number. It's my third number. Then you move the storage variables down by 1, but to offset that, you just make this 49. Okay, and then as you add variables, as you take up storage slots, you just decrement this accordingly. This is one of those solutions, and as I mentioned before, the other solution is to use namespace storage, which provides more upgrade possibility, but at the same time it increases complexity, and with complexity there are more ways to mess up. So usually people just opt out for this one by using a storage gap in the parent contracts, and as they add variables to the parent contract, they will decrement the storage gap accordingly to make sure that the offset is maintained inside the child contracts. And that is all I want to point out. Hopefully you learned something from this video, and hope to see you in the next one. And thanks for watching. If you have any questions, feel free to leave some comments and join me on the Discord, and hopefully you enjoyed this one, and I'll see you in the next one.